Hey everybody, Dr. A here, and in this video we're going to be exploring another example of developing an equivalent system. But before we dive into it, don't forget to hit like and subscribe and be on the lookout for other content like this. Alright, let's get started.
In this example, we're being asked to replace the loading on the slab with a single resultant force and then to specify its x and y coordinates. So I'm going to go ahead and draw this out. This is going to be a 3D type of problem. So this is all given information. Here's a y-axis here. X-axis. And a z-axis. Okay, now I'm going to draw a slab. I'm going to try to draw this in gray so it's like a concrete slab. And we're going to go out about 20 feet in this direction, another 20 feet in this direction. There we go. Okay, please forgive my poor artwork. Okay, I'm going to show a little thickness there. All right, so this is like a concrete slab, okay? And I'm going to go ahead and put my dimension lines on it. So we said that this dimension was 20 feet, and also this dimension is also 20 feet. And I'm going to have the following loads. In this corner right here, I'm going to have 25 kips. On the back corner back here, that's right on the y-axis, I'm going to have 15 kips. Maybe there's a column there, who knows. And then I have something acting right here that's going to be 5 kips pulling up. So maybe I got something that's pulling up on the slab, okay? And then the location of that 5 kip load is going to be at 15 feet along the positive x-axis. All right, so how do we get this process started? The first thing I'm going to do is compute the resultant force. So that's the easy part. We're going to say the resultant force, F sub r, take off that arrowhead, magnitude of the resultant force, F sub r, is going to be equal to the sum of the forces in the z direction, and we'll call up as positive, and that's going to be equal to 5 kips minus 25 kips minus 15 kips. So hopefully we can do that in our heads and see that it's 35, but just in case we can't, let's double check that in our calculators. Oh, surprise, 35. So it's negative 35 kips, which the negative indicates that it is pointing down in the z direction. Okay, so this thing is acting downward somewhere over here. Okay, so here's what I'm gonna do. I'm gonna try to redraw this. So we're gonna say draw the equivalent system. Okay, here is that y component or y direction. Here's x. Here is z. And let's go ahead and draw our concrete slab. Okay. There you go. All right, so where is that equivalent force? Well, it's like we said, it's somewhere here, right? F sub r equals 35 kips. I'm showing it pointing down. But the problem, not only did the problem ask us to calculate the resultant force, but it said what are its coordinates from the xy plane, right? So what we're also looking for is this coordinate right here. This is the y coordinate, all right? And then we're looking for this coordinate here, the x coordinate, all right? So how do we do that? Well, this is where we're going to apply moment equilibrium about each of the axes, about the x and y axes, to figure out those distances, all right? So here's what I'm going to do. I'm going to say apply moment equilibrium, all right? So what I'm going to do is I'm going to say sum of the moments about the x-axis equals the resultant moment about the x-axis, okay? And just very similar to what we did in the previous example, we're gonna look at the moments generated about the x-axis in the original figure, okay? So we'll make a note here. We'll say this is from original system, and then we're gonna look at the moment generated in the equivalent system. And when we do that, we can build in the perpendicular distance of y. So again, if we're summing moments about an x-axis, what is the distance, what's the perpendicular distance away from the x-axis? It's along the y direction, all right? So keep that in the back of your head. Let's look in the original system, all right? In the original system, is the 5 kips going to generate a moment about the x-axis? I'm going to tell you the answer, so I'm going to ruin it for you. No, it does not generate a moment about the x-axis because it's on the x-axis. But what about these two forces, 15 kips and 25 kips? Absolutely. What are their perpendicular distances away from the x-axis? In both cases, it's 20 feet, okay? So I'm going to say, I'm going to establish a direction, and I'm just going to say, looking in the xy plane, if I have a counterclockwise positive, then in the YZ plane, counterclockwise positive. So I'm going to be looking at like this kind of directionality. So this will be like a negative, okay? So we're going to say 25 kips times 20 feet. That would be a negative, and then minus 15 kips also times 20 feet. All right, so again, we got 25 kips times 20 feet, 15 kips times 20 feet, and again, each of these are causing a rotation about the x-axis going clockwise, so that's why I put a negative in front of it. And then we are going to do a similar kind of thing, but on the right side of the equation. So on the right side of the equation, we will still say we're still going to say counterclockwise positive, and in the equivalent system, we're going to say F sub r times y, and again, that's going to give me a negative value because it's causing a clockwise tendency of rotation about the x-axis. So we're going to say equals F sub r times y. But remember, we know F sub r, right? We calculated that. F sub r is 35 kips. So doing some rearranging, same operation we saw in the previous example, the y coordinate is going to be the following. We're going to say 25 times 20 plus 15 times 20, and then divide by 35. I forgot my negative there. The negatives cancel, and I get a value of 22.85 feet. Okay, put that in your back pocket, and we're going to do something similar. We're going to say some of the forces, some of the moments in the about the y-axis equals the resultant moment about the y-axis. And in a similar way, let's look at the original system. Let's take a look at how these forces are causing rotations about the y-axis over here now. So we got 5 kips. If I look in the xz plane, I got 5 kips causing a clockwise tendency of rotation, and I have 25 kips causing a counterclockwise tendency of rotation. So I'm going to have -5 kips times 15 feet plus, what was that value? 25 kips causing, times 20 feet. So 25 kips times 20 feet equals resultant force, F sub r. Now, when it's rotating, when F sub r is rotating through this distance x, it's going to cause a counterclockwise tendency of rotation, so that's going to be positive. And we're going to say times x, okay? And again, this is 35 kips, and then we can solve for x as the following. -5 times 15 plus 25 times 20 divided by 35, and I get 12.14 feet. Keep track of your units. X should be left with feet, so should Y. Let me double check my directions one more time, make sure I'm not making any careless mistakes. 5 times 15 clockwise, 25 times 20 counterclockwise. Yep, that should be fine. And then 35 times x counterclockwise, so that's positive. Yep. So the coordinates are chords of the resultant force are 12.14 feet, comma, 22.85 feet. Now, you may be wondering, you may be looking at this, and you may be thinking, well, wait a second, this seems a little weird because the y coordinate is 22 feet long, right? So you may be thinking, well, you know, these dimension lines were 20 feet and 20 feet, right? And we actually calculated that this force is actually like over here somewhere. Now, is that possible? Is it possible that the equivalent force is off of the slab? Yeah, it's possible. It's kind of weird, and in a structural design problem, you would try to redesign this such that that doesn't happen, but it is statically possible that your equivalent force is off of the system, okay? Now, what would that physically mean? Well, that means that if you just kind of look at how this slab is arranged, what that implies is your compressive forces that are pressing down on the slab are on this edge, and then you have this upward force on the opposite edge that is tending to make this slab want to uplift and rotate over. So it's kind of like something is trying to pry this slab off the ground, and that's what's shifting that equivalent force off of the slab. So in a design scenario, you would really analyze the slab for this situation, and then you would redesign something. You would redesign the geometry of the slab such that the slab isn't trying to lift up off the ground. But from a statics perspective, this is possible.